going to talk about this foamNewApp utility, how we can use this utility. So basically this utility it will use to create the basic create the template, create the solver template. So we can see today in detail, then we will create one solver, and then we can try to see one I will try to demonstrate one problem, so which we will create, which we have created that solver by using that solver. So like I have mentioned here, we will use this form new app utility. So if you want to know more, then you can just type in the terminal form new app in help. So then we can see in the later on in the tail. And so like I have mentioned here, my whatever I'm going to demonstrate here, so then I gave the name for that solver, so that I have given this the name my t form, basically now I will see later on in detail. So that is the plan for the today's demonstration. So let me tell about this form new app. Basically this utility it creates a solver. Creates solver template in OpenFOAM. So we'll see this later, how we can, I will try to demonstrate how we can create this how we can use this utility, and we can get that some advantage. So we'll see then in next slides. So that if you want to see, if you if you open the terminal, then source the OpenFOAM. So the OpenFOAM, which version you are using, then just type form new app and then space hyphen help. That it will display all the option whatever it's contains, so you can use it that. So for that, this we will see this we will see the application of this new form new app utility. So like in the here I have mentioned one picture here. Basically that is the solid slab. So then solid slab, so then we can see like this is solid slab. So suppose that it has some wall temperature is heated in the temperature, then how the energy transfer from surface to this slab, we can see in detail. Yeah, now hello, like I said, I will consider one problem which I will demonstrate by using new form solver, which we will create in OpenFOAM. So that like I have given the name of that my solver, which I'm going to create as a demonstration purpose. So like I have given the dummy name here, my t form. So basically this it will solve the physics of the it will solve the physics, like I have mentioned here. This it is used for an steady state simulation computation, and basically it is for a heat transfer in solid through the conduction mode. Basically, as we know, the heat transfer, there are three modes of heat transfer: one convection, conduction, and radiation. So but we are not like I'm going to demonstrate, and yeah, just I'm considering for the demonstration purpose the only the one mode of heat transfer, like conduction mode. So like we'll see in the later on. So like yeah, I'll demonstrate that in detail. So like I said this I have already described here. So form new app utility used to create the solver template. So and this work like a pre-modified solver. So pre-modified, like when we create the solver, just we can take it as a reference the existing solver, then we can add it based on our problem, what problem we are going to solve. So based on that yeah, so if you see there, when we have this solver, so solver directory, so then it contains some file and directory, like it contains some for solver names file, and another is the one make make directory. There is in make there is a two file, option and file. So I'll explain just later. Just I'm giving the some brief intro okay, what I'm going to do here. So what is the advantage of this WAP you are using? Then so by default the we don't need to change the environment, but when we have the our existing solver in the source code, the all the this environment variable this in this form $form underscore append win. So when we are using this as a user, so then we have to change that this environmental variable. So then you don't need to change when we use this and when we use this utility foamNewApp, so it will by default it will give this, so you don't need to change. So we will see in the later. So that is the basic. So now I'm just giving this just brief introduction what I'm going to do here, and then we will see in the detail. I will demonstrate this all the whatever I'm going to talk. So we have this environmental variable like fRun, so foam underscore run. So basically we know this is run, this is basically environmental variable, and you can do also you can use the run. Simple open the terminal, then just execute the run. It will take you the run directory. So basically run directory. And we have the another case, so we can in the second for the demonstration side, so we can take one tutorial case, so then we can, based on that we can modify it, or we can just and now I said, then I'm going to use this basically then heat transfer, because there is a diffusion equations we can use 1D 2D, it depend on the problem specific. Now we have this I've considered this equation for the demonstration purpose today. So I will talk about, and first we will form the this solver for this equation, how we can solve this equation by using OpenFOAM. So basically today's funda, I will create one one solver for this, which we have seen. I have said earlier, so I have given the name of the solver is mighty foam. So basically we are going to solve this equation, so by using this OpenFOAM. So I will continue this later on when I'll just now. This is the brief, basically this is a brief what I am going to do. So now I will demonstrate all the things whatever we are going to do. We have to use this. First I'll show this how we can use this, and this is the second part of our today's talk. So now let me show this first. Just now let me open the terminal first. So as we see now, just I have to source my OpenFOAM. As we see, there are several OpenFOAM version are installed in my machine, so I am taking one of them. Today I am just consider this community version, OpenFOAM community version, which is the latest version of OpenFOAM 9. Yes, just as I said, if you execute this command, it will take you the run directory, or if you say where is that this you can do, you can see. And there is another option. If you do foam dot run, so then oh, that is a mistake, so I left with the $sign. So, and if you do pwd, then you can see the both the way you can go, you can reach to this run directory. Then just run, because these are the environment variable which is set in our system. So now just let me clear this screen. So now we are here now. So now our motto is, first we have to use this utility. How we can use this utility? If you if you want, just type foam and new and app, so it will give the help, it will show some help. Okay, now I'm going to use this utility. I'm creating my my template, my solver name, just I'm using this foam and my foam, yes. Now as you can see in the status, so it's saying creating application code directory my t phone, which is the my name of my solver, which I'm going to which I have created just now. So then we can see what inside now, what is inside this what is inside this. Let me first cd my t my t my t form. So you can see what is inside the this t, no t minus l and 2 you can do. So you can see whatever this is basically my home directory or my this is a home directory of my solver. So it contains, it says if you execute this tree, then it will display the how many directory and file contain in this directory. So like it says one directory, basically one directory and four file, one file 1 2 3 4. Yeah, these are the four file are created. As we can see here, just let me show. Then when we use this utility, what is the benefit of this? Just let me show this make and then you can see here file, their file is, yeah. So as we can see, there is already this is user defined. Basically this environment that you don't need to change. Basically this is when you use this utility, it will create this so it will take care itself. So that is the first advantage of this. And just let me go out and we can see, and it will create this create fields header file, which basically when we in this file create field, we have to define the all the transport properties and the field variables which we are going to solve here. Like in this problem, in this problem, what is the field variables, what is the variables are here? Only the temperature is the field variable here. And another option, there is some property or that the transport properties, like this the alpha. Basically alpha here, what is the alpha here? Thermal diffusivity. Yeah, your thermal diffusivity, basically transport properties. So that is a two here. So we have to define all the this temperature field and this alpha thermal diffusivity. And we can have a look this what is inside this create. So create header file. So basically when you use that by default it will create the field this field field variable for press this pressure. So you can see here, yes, you can see here. So now just let me go out. So that is the benefit of this utility when we use. Now second point is, now what now we have to write an equation. We have to write we have to write the equation. We have to the right equation in this form. How we can, just let me go first in this just let me just give me one. So like this is the like we have recently we have created this. We can see this what inside this, see. So like we have shown this is a pressure and this field we have to change. We have to write the our equations here, all the so first we have to add the we have to add the equation which we have to solve, and then we have to write some field variable we have to create the field variable in this file. We have to define the what we have to define here, this transport property and field. All field variable here is only we have only the p, only the temperature here. Like we can change the temperature, and we can see the temperature here, temperature, and we have to change here temperature, because that is scalar, because volume is scalar field, because temperature is a scalar. Yeah, so then pressure also is scalar. We can use this this we have created. Now another option, another what we have to do, we have to add the transport property. So let me it will take some time, so I will use some I have created something. just one second. uh, let me add some. I have prepared, because if I do everything here, it takes more time. So here, like, we have defined the thermo. First we have defined read this transport properties, like we have in the, like we have the standard format of the OpenFOAM case, like we have the time directory, zero directory, and constant, and system. With constant folder, it has the all the thermo transport property. So, and what is the transport properties here? Transport properties here, alpha. As you see, this is the transport properties alpha. Here we have to, like, when we have defined the thermal this property, so then because this is the scalar, so we have to define like that. This is basically, you can get, this is the basic standard format. So yeah, we have defined. Now thermo, we have to read this. So transport properties, so then we have defined alpha. Yes, and another we have temperature. That's it, nothing else we have to. Just we have two things here add to add here. So another now question is, now we have to add here, we have to add our equation here, like this equation, like we have the mesh, like we have the geometry is basically different elements. So that different element, so then there are basically different, so then we have to use this some looping here, like if you see any tutorial case, then you and solver, you will get all the information. So but because of time is time limit, so I will take care some, because I have prepared here some case already for this. Just let me show. So now, like we have the this time, so then we have to start this time looping here. So then we have just we are and just inputting this time. So then, like, we have to define the equation here, like we have the temperature. Basically, when we have the equation, like we can write this in this format. So that basically for the demonstration purpose, so I prepare this for the explanation. So there is a, like, this one, then equation, then equation we can write the like a function. So when ft this if we like we have this equation, then we can write in this format, right? This equation basically temporal term, and this is the diffusion term. We don't have the convective term here, so only we have two term here. Then what is this is a temporal term, then which is define the because this, when we use this is volume one, because this is a finite volume method approach, right? So then we have to write like that, that is standard format. So this is the time temporal term, and this is the basically this is a diffusion term. So diffusion basically this is a Laplacian of the temperature. So then we can write like that. So I have explained here. So there is a two way here. Either you can save this equation in the another file, header file, so you can include here, or either you can just like let me there are two way. One way is this, and another way is this. So I have just now just one second, I have to uncomment this. This is the first way, like we are going to solve this equation. So we have written this equation here. So yes, now because this is the standard format, we have to write all the time step. Yes, so then we have considered those, we don't require this one, then we have to close the loop. Basically that is the equation we have consider in this loop, and nothing else. We have only it is by default, it will take care that utility, so you don't need to change anything. Let me show subs. I have to save first this one now. So as you see now, see this and this just this one. Yes, now let me now, and what is the standard procedure to run any, just let me just see. So what is the procedure to execute the any execution? So first we have to clean, we clean. So just we can clean, and and how we can execute, just we have the right bmake, we can execute bmake command. So uh, so it will execute the your solver. So as we seen here, there is no error is getting, mean we whatever we have written here, we have written here, all are correct. Let me yeah, so if something is wrong here, so it you will get the error here, you will get error here. It will yes, it will, you can see here. Now if you want to test this, just open it this if you want to test this, just source it, open and my what is this, if you my t foam, yeah, it says yeah, it's correctly working, because here is the error because we have not defined any it is the standard, there is no, because we have not any case, we have not prepared any case now. So now this is one task is done, solver is made. Now we have to now see next, we have made this solver. So next this one, and we have to copy one we have to copy one any cache from your source solvent, this OpenFOAM source file. So you can copy it this one, like I'll tell you how, just just 1 second, give me 1 moment. Where are we? Just we can go out now, and just we can go out or just run. Now we are in the run directory, right? Now see, just we can copy here one file, one this one this tutorial folder for this, basically the when we have a tutorial folder and in comparison and IcoFoam. Basically we have taken one to one case, tutorial case, which IcoFoam, basically IcoFoam is the tangent solver, that's what we have considered is yeah. So if you copy here, then you do ls here, then we have copy here this one and this one. So this cavity form, similar way mein, this one, and this I have already copied, and just I have made some changes here in this. So we cd slab this, I have copy that folder and I made some changes. We can see what is there inside that. So and you can see here there are C and what inside this is the temperature, like we have only the, like I said, we have the only the temperature. So we require the temperature file here. So what is inside this, let me show. So basically we have this define the, basically it that just 1 second, let me explain here. Like here because we have copied that template from the IcoFoam, so then I have not changed the name and all. So just we have I have consider this like this, it says is moving ball. Basically here the solid all the wall are fixed. Basically it's name it depend upon you, we can change. Basically all the wall, these are the file, these are the 3 walls are these are the fixed wall, and this one is main, this basically boundary mentioned. You can change, but I have not changed because I'm following the template. So it's basically this boundary condition totally user specific. You can give the any name based on your choice here. So and this is the, because that we have taken we have taken from this so it means we don't have here that we have a wall here. Only the wall is the fixed wall, fixed condition we have defined in the fixed wall. Fixed value, basically fixed value when we have some temperature. This wall are these all the four walls are at a particular temperature, like I have mentioned in the temperature here. Then internal temperature is like I have mentioned is 25 degrees centigrade, which turns around 2098 or 98 Kelvin. So that is the only the temperature here. And fixed wall, we have I have kept this fixed wall 315 and 315 Kelvin, and which turns into 40 degree temperature, and that's it. So we can go out this one. And what we have here, just we have to go out here ls, and let me show what inside this. Just let me visualize first 3 minus L to regulate. So there is a some this file, and this block mesh basically it will create the geometry. I'll show you geometry and control directly. Let me visualize everything so you can get some in. And so first I have done this one, and I have to show the transpose properties here. So just where is that? In constant folder. Vi constant, constant and transport properties. So then you can see here like we have the transport property, the thermal diffusivity alpha. So we can define when you copy from this source come to the tutorial for the tutorial folder. So it's it will show here, it will give the mu yes, viscosity, dynamic viscosity. So but we here in our case with thermal diffusivity. Yeah, this just let me go out here, this one case. So another, and what we have changed, we have done this the temperature file, this transport property file. Now we have left with the this one. What we have done, just let me show you. Vi system block. What is this block? Basically block mesh utility. It will create the mesh basically. Yeah, you can see here all the information about the information here. So but I have considered here, like I have just refined the mesh, only this modification, I have done here, nothing else. Basically that you will find in the tutorial case. So next what we have the control dict. Yes, bi system and control, which we have to define all the, yeah, like I have changed this my this solver name, and yes, it's 100 second, and this nothing else. You can see here, nothing is fancy here. And scheme, I have to show one scheme also. fb just system fvn. So as you can see that this is the this is the transient simulation. Then we have used this and we have defined the gradient string. So this gradient type linear equation, linear, and we don't have this divergence scheme, and we have the Laplacian equation for, we have the Laplacian. So we have to define here. You can see and compare that this gravity this cavity tutorial. So you can see what modification I have. So these are modification you have to do here, and we don't have this divergence term. Then we have the Laplacian, we have to change it for the temperature. So that's it. These are the some modification I have done. And what we have left, with this happy system, BA system happy scheme solution. Oops, happy solution. So what, and you can see we have only the temperature here. So we have temperature, then I have changed. If you compare with this this file with this cavity tutorial, so you will find the difference. So basically we have only the temperature here. Yeah, we have defined the solver. we are using the here the smooth solver. Yeah, so nothing else. uh, Now everything is set. Now what we have to do now, so now what command we have to use. First we have to create the geometry, then we have to run the solver. That's it. This how we can create the geometry. Just type uh, block mass utility. As you can see, the all the information about the geometry. Yeah, these are the fee patch, all the information. So let me show you. Foam parafoam minus world, and when we put this end, then it will run in the background. Let me show you the geometry first. So this, yes, yeah, you can see the geometry is here. This is the 2D geometry, 2D case. So then you can see here, so all the patch information, and because we don't have the field variable here, because we have not yet execute this solver. So if you want to see, then we have to run that solver. Now what is this? Now what the solver name is? My T foam. If you run this, then you see all the iteration is happening now. So we can save this log file, we can save this all iteration in the in log file. This basically I have run for the time 100 seconds. Then we can see then what also the this what inside that is. You can see the time directory. Now in the directory, this is the time directory 0 to 100 seconds. What how the temperature is changed in this solid slab. So then we have this. Now let me show, let me so big one. Now just we have what we have to do, just we need to do refresh, we have to do refresh thing. Just if you refresh, then you can notice there are time this field is loaded in this para view. So if you want to see the diff in the temperature, so it just one second, we have to it will show here. This is the temperature. So this is the temperature. Let me show let me select another this. Yes, and just let me just surface, I have to see that the temperature at the just let me show another thing, one more thing. This that we have to remove this. We can change this the font size, and we can change the font size, and whatever you want you can write. And like temperature, you can write the unit of this. Suppose this is the in Kelvin. Yes, and this yes, and you can also change this 24, and you can also length of this it's 80 length of this bar, this level bar. So just open, you can see here. So now and we can see the time, just how we can activate the time. As you can see this so then you can select the time filter, so that if you execute, then it will show here. When if you want to use some second and another thing, you have to this 0.3, like 0.3 mean it will take care of this up to 3. And if you put the second, it will show here the second here. So then if I'll change the background here, is white, we will take white, then we can see how this temperature is changing. So now our case, so this the time you can see, and let me just, you can see here the temperature changes here. So after, because you'll see after 38 seconds in temperature are going to constant basically. Yes, you can see here. Yes, if you take the, because temperature is, because it's getting a steady state now. So You can see here, you can see after 10 seconds there is a very little, almost same temperature, it's reached the steady state. So that's we can see the energy, basically this energy how it's transferred into the solid by the this is a conduction mode, heat transferring through the conduction because it has the thermal conductivity. Yeah, so let me save this first, just 1 second. Slab, yes. Now I'm going to minimize this, so let me come back here now. So what I have done, I have demonstrated this one. Let me summarize this what I have includes today's demonstration here. I have demonstrated this how these utilities work to create the solver template, and one one tutorial case, and this we have considered this equation. It could depend basically if something, so it depends upon what you are going to solve. Based on that the complexity will come. So if suppose if you consider this one, because here the temporal term, diffusion term, another some extra force, extra source term is extra forces, how much what is the extra term, like in this case suppose you can zoom the heat generating source term, and you can have this convective term. So that is depend on the problem. So like these are the case setup. I have written all the steps whatever we have follow and which I demonstrate here. So like we have convert copy one tutorial case from the source of in OpenFOAM. So then we have changed this name. So based on that we can go in, we can move go into this this our case. So in that what we have to do, there is a term like we have the standard zero constant system. So there are the file content which I already showed you. Then you have to do some modification here. So then yeah, after then you have to create this geometry like block mesh utility. After that you have to run this run this our creator solver. So after that this one is nothing else, that's you can type basically what if you run this, then it will open the para view in terminal. So that if you create this torch, it will create the dummy file, and dummy file then you can open into the paraform para view. So that's it. So like I've defined this the all that these are basically the problem definition. So we can see here the temperature. So like this one temperature you can see here. I'll show you just 1 second how this only just you have to change, nothing else, just you have to change this one. You can get the similar kind of results if you change that this one these color preset. So you this one you will get the same kind of results. So like which I mentioned here. So now these are the some links you can follow, and you get some information and explore your information. Yeah, so um thank you for watching, and yeah,